We're going to spend a few minutes today giving you an outline for your test that's coming up on Tuesday on uniform circular motion. And some of these things are going to be straight from the assignment that you guys handed in earlier today. Okay, some of these things are not going to be straight from the assignment. They're going to be a little bit more leaning a little bit more towards the multiple choice portion of the test. Okay, this should cover the test. Now, it's not going to cover specifics within multiple choice, but still general concepts that you should be aware of for those multiple choice and for the written questions as well, for that matter. We define uniform circular motion, UCM, uniform circular motion, motion in which the object is going in a circle at a constant speed. So remember, the only thing we got to really take away from this is that we're going at a constant speed, not a constant velocity. Okay, because the direction is changing, but we're talking about a constant speed because it's not speeding up or slowing down. You got to be able to define frequency, period, and speed and know how to find them. Okay, you know that frequency can be found by saying it's the number of cycles over the time. The period can be found by saying the time over the number of cycles. And of course, the equation that relates the two together that appears on our data sheet looks like this. T is equal to 1 over F. We also have speed, which appears on our data sheet. In the context of circular motion, we'd say that V is equal to 2 pi r over T, the circumference of the circle divided by the period. Now understand that we started the unit with these terms, and we did questions involving frequency and period and speed. But understand that these terms, frequency, period, speed, they all carried throughout the unit. So we may very well have a question as late as yesterday. In fact, we did have a question as late as yesterday, the last day of new stuff in the unit, where we still had to use this equation, V is equal to 2 pi r over T. So you're not necessarily looking for a question that says, oh, the record player makes this many revolutions per minute, what's the period? You might be looking at something like that for sure, but you might be looking at a much bigger question involving a satellite or involving probably not vertical circular motion in this context, but centripetal force or something like that, where you got to find the speed or the period or something like that. Okay, so be aware that these equations go all through the unit, not just at the beginning of the unit when we did them. Centripetal acceleration, centripetal force. Remember that centripetal means center seeking. So remember that the acceleration, centripetal acceleration, centripetal force are both directed toward the center of the circle. If we draw an object going around in a circle like this, okay, it's going around, let's say, counterclockwise like this. The velocity, let's say at this moment in time, the velocity of that object is at a tangent to the circle. The acceleration would be toward the center of the circle, and the force would be toward the center of the circle as well. Be able to calculate the centripetal acceleration with an equation that appears on your data sheet. A is equal to V squared over R. And be able to find the centripetal force, which is mv squared over R. And remember that these equations can be standalone equations. You may just have to find acceleration given V and R, the radius of the circle, but you may also have to find V to put into there using 2 pi r over T, or you may need to find T using 1 over F, and then find speed using 2 pi r over T, and then find acceleration or force using the equations that we have at the bottom of the page. The centrifugal force, of course, we have that in quotation marks. How come? Because it's not really a force, right? It's the force that pushes you out towards the outer edge of the circle, but it's not really a force. What is it that pushes you towards the outer edge of the circle? Why, when you're on that merry-go-round close to the center of the circle, why do you end up being flung out to the outside? One word. Inertia. Yeah, centrifugal force is really just inertia. Now, the reason when you're pinned against the wall, when you're going around in the circle, that you feel like you're being pushed out is because of inertia combined with the centripetal force pushing you in, right? When we have that force pushing you in, we experience that, we call it a pseudo force, a fake force pushing you out. But really, in the end, it still comes down to inertia. You have that so-called centrifugal force because you really want to go in a straight line, which takes you to the outer edge, right? Sometimes the wall pushes you in, making you feel like you're being pushed out. Sometimes you just end up going out because of inertia. Then we talked about vertical circular motion. We have to analyze the top of the circle, the bottom of the circle. So at the top of the circle, we'd have a normal force and a force of gravity. At the bottom of the circle, we'd have a normal force and a force of gravity, but in opposite directions. Remember, in both of those cases, we have to draw the free body diagram. It's so critical to do that, to draw that free body diagram, because if we don't, we're likely to miss the next step, which says F net is equal to the sum of the forces, Fn plus Fg, the normal force plus the force of gravity. And then, of course, mv squared over r is equal to Fn plus Fg. We're often in these questions asked to find the normal force. Okay, Fn is the normal force. But another name for the normal force could be the force of the floor, or the force of the track, or the force of the string, if it happens to be a string pulling on, say, the keys going around in a vertical circle. Fn also corresponds to, as you saw in your assignment that you handed in earlier today, it also corresponds to your apparent weight, how heavy you feel. How heavy you actually are is your force of gravity. But you're not likely going to find the force of gravity using this equation. You're probably, to find the force of gravity, just going to say m times g. We need to be able to find that normal force. We also need to be able to find a minimum speed. When we're looking for the minimum speed of an object going in a vertical circle, we're looking at the top of the circle, because if it's going to fall out, it's going to fall out at the top, right? When we're looking for minimum speed, you're going to solve for speed. At the top of the circle, and you're going to make sure that you make Fn, the normal force, equal to 0 when solving for that minimum speed. What kind of question are you going to be asked about Aristotle, Copernicus, about Kepler? You know, if that appears, it's going to be in multiple choice, right? We spent so much time on Kepler's laws, not like days, but we spent enough time on Kepler's laws that you got to be fairly confident that that's going to appear on your test, right? And if it appears, it's going to appear in multiple choice. So there's some good multiple choice questions right there on Kepler's laws. Okay, could be the other stuff as well. Aristotle, remember, geocentric theory of the universe. Okay, everything revolves around the Earth, including the sun revolves around the Earth. Copernicus, a couple thousand years later, heliocentric theory, which says the Earth and other objects, other planets revolve around the sun. Tycho Brahe, a little bit later on, he's the P guy, right? P guy, missing nose guy. Tycho Brahe took observations, naked eye observations of the motion of planets and stars and so on, and then his assistant, Johann Kepler, devised 3 laws that described the motion of the planets from the data that him and Tycho Brahe took. The 3 laws, remember the laws of elliptical orbits? The law of equal areas, which said here's the sun, right? Here's a line joining the Earth to the sun. Over here, line joining the Earth to the sun sweeps out equal areas in equal times. And of course, the 3rd law, which was the law of periods, talked about this constant that we call Kepler's constant. Okay, that's useful for what we call a central body. When an object is being revolved around, the square of the period of revolution of whatever it is that's doing the revolving, divided by the cube of the average radius of revolution is equal to a value, constant, a Kepler's constant we call it. Now, that Kepler's constant is the same every time something revolves around the same object. So the Earth revolves around the sun, Jupiter revolves around the sun, Neptune revolves around the sun. All of those, all of the T and R data for all three of those planets would produce the same value of K for the sun. Okay, Kepler's constant for the sun is the same no matter which object is doing the revolving around the sun. Then we went to Newton's universal gravitation, which, remember, is that force of gravity that acts between any two objects with mass. We talked about the torsion balance experiment. Remember the torsion balance experiment? The purpose was to get the value of G. Looks something like this, right? You got a string hanging from a ceiling. On either end of the string is a mass. On one end, we'll call it mass 1. We bring another mass 2 nearby. There's going to be a force of attraction. We measure the force by how much the string twists. We measure the distance that separates them. We measure the values of the masses. And then we turn around and use Newton's law of universal gravitation to solve for G. So we use F is equal to G m1 m2 over r squared, solve for the value of G. And Cavendish would have got a value that was very, very close to the accepted value of 6.67 times 10 to the minus 11 Newton meter squared per kilograms squared. It's on your data sheet, so you don't need to worry about remembering that number or the units for that matter. We need to be able to find the force between two masses. So that's going to be F is equal to G m1 m2 over r squared. Make sure you're in the right units. Make sure you square the distance. All of those little things. If I'm looking for the force, let's say you got object number 1 and you have object number 2. Okay, number 1 and number 2. If I'm looking for the force of gravity between these two objects, I use this equation to find that force of gravity between the two objects. If I'm looking for the force of gravity on number 1, I use the same equation, get the same force. If I'm looking for the force of gravity on number 2, I use the same equation and I get the same force. The force is the same whether you're talking about the system, object 1 or object 2, it's the same value. So you use the same equation regardless. You've got to be able to do it with 3 masses as well. And this is what we had our quiz on today. Object number 1, object number 2, object number 3. Okay. Be able to solve for the force of gravity on object number 1 or on object number 2 as a result of the other two objects, the other two forces. In other words, the net force is equal to the sum of the forces, just like we did a lot in our last unit. The difference between a force and a field. Remember, a force requires a producer and something to experience it, whereas a field, this region in space in which a force of gravity can be felt by an object with mass, it only requires a producer. Field requires something to cause it. Force requires something to cause it and something to feel it. Of course, we have 2 equations that go along with it. There's the producer equation, Gm over r squared, and we have the experiencer equation, which is F over m. Be careful about a couple little things here. Make sure you use the correct mass, mass of the producer, mass of the experiencer. Remember that force of gravity here is also sometimes called the weight of an object. So if you see the term weight, it means the same thing as force of gravity. You can sub it in there. Make sure you square the distance r if necessary. And make sure that r is measured from center to center. And what do I mean by that? Let's say you're given a distance from, here's the Earth. Let's say you're given a distance from here to this spot where you're trying to find the field strength. You need to add this distance to the radius of the Earth in that case, because you need to have the distance from center to center. So if you're given the distance from the center of the Earth or whatever planet it is already, great. If you're not, then add the radius of that planet to it because you need the distance from the middle of that planet to wherever it is that you're trying to find the field strength. And then finally, you got to know what a satellite is, right? Satellite is something that orbits around something else. We talked about this one yesterday. Orbits around something else, held in place by gravity. So whenever we're dealing with satellite motion, we're going to set Fc, the centripetal force of it going in a circle or more or less a circle, equal to Fg. mv squared over r equals gm1 m2 over r squared. Remember that one of the r's cancels, one of the m's cancels, and I'm left with v squared equals g times m over r, m being the mass of the producer. That's the one that's left. Now, just like I said, when we first started this little outline, this little review, I said we learned an equation for period, frequency, and speed. Sometimes you got to use that equation for speed in here, right? Sometimes you got to put v is equal to 2 pi r into this equation in order to get what you're looking for. Sometimes you might need to find t by using t is equal to 1 over f, and so on and so on and so on. So this is not, even though we did this yesterday and last thing we do, it's not a standalone topic, right? It goes with all of the stuff pretty much that we've done this unit, literally right back to the first day where we did t is equal to 1 over f and v equals 2 pi r over t.